I don't know what Europe is because the boundary of Europe is moving eastward, eastbound. How many? Give me an answer. How
2
many?
or 3 for each person.
2 or 3 for each person. 300 million persons means 1 billion AC adapters. Let's suppose you say 1 watt for each AC adapter because your efficiency is higher. It means that you, and the AC adapters usually are left connected to the mains all the time. Me included, I do the same. I don't disconnect the AC adapter when I finish to recharge my cell phones. And AC adapters, or something similar to AC adapters, are also inside, let's say, your TV set. Your TV set, when it's off, actually has still a power supply running because it has to wait for the remote control commands. In your PC, desktop, even if it's off, inside the box, there is a small AC to DC converter, or DC to DC converter that gives you a 5 volts uninterrupted. Even if you switch it off, you still have 5 volts inside the computer. So, 1 billion of this, 1 billion watts saved means one large electric production plant that you don't need. There is one large electric production plant, 1 gigawatt, that could be saved just improving the efficiency of these AC adapters. And then you have all the green people saying, oh, pollution, power plants, etc. Well, just disconnect the AC adapter, and if everybody does the same, you have one less large power plant needed in Europe. So, power saves. That means cost. You don't have to pay a larger bill. Telephone. Why we want a high efficiency? It's still the same story, but we see it from a different point of view. When I gave you the example of your desktop, I was imagining a situation where my primary power is unlimited. I mean, from the mains you can get all the power you want, all the energy you want. If your power supply wastes 25 watts more than another, who cares? You have, you will pay 25 watts more times the time you use it. You don't have so much power saving, but it's not a big deal. The problem is when your energy is not as cheap as your mains energy. How much is the cost of the energy, the electric energy from the mains? Give me an estimate.
20 cents for watt.
20 cents for what? No, that's too much. Kilowatt hour. You pay the energy, you don't pay the power. So 20 cents for kilowatt hours. It's not a big deal because 25 watts, it's a fraction of a cent per hour. But story is different when the energy costs a lot. Give me an example of an energy that is absolutely awfully expensive.
Battery.
Battery. Any battery has a cost per energy that is at least 3 orders of magnitude larger than the mains. The energy you get from a battery is on the order of $20, 20 euros for kilowatt hours or more. Could be 3 to 4 orders of magnitude. So in this case, the cost could be an issue. The cost of the energy. Not only because you need to buy new batteries, or you have to, you don't buy batteries anymore too much, too often. What do? You recharge it. You recharge the battery. Because when you recharge the energy, your object that is portable, that has batteries in it, cannot be moved away anymore. It must be hooked to the mains. And so, if your cell phone, oh by the way, I forgot to switch my cell phone off. If your cell phone has a bad energy efficiency, it means that this battery will last a shorter time than another better cell phone. And if your competitor manufactures a better cell phone on the market, your competitor will win the market. And your company will fail, will break down, and you will get out of job. That is right, because you are not smart enough to design a good power supply for your cell phone. The third reason why we want high efficiency is in the battery operating environment, let's say portable devices, is longer endurance. Your system works longer with the same battery. Or your system works the same as a competitor but is smaller because it has a better efficiency in the energy. Okay? So that's basically the reason why we want high efficiency. And as far as I know, the only way to get a high efficient power conversion is to use switch mode conversion. And this will be our main subject for all the class, switch mode conversion. That means let's put a comparison between switch mode conversion, that I will define in a moment, and the standard way you have to convert a voltage, for example, using a transistor working linear region. You can have linear, I don't say conversion in this case, linear power supply that means here we have transistor used as a linear component. You had classes on, you saw the linear power supply, linear voltage regulator in the previous classes, did you? More or less.
More or less.
Well, the basic idea to have a linear power supply, linear voltage regulator is to take a transistor like this. I use a bipolar transistor, but you can use every transistor you want. Here you have V in, the input voltage, and you want to control V naught at the precise level, and this is your load. Well, what can you do? All electronics or analog electronics works using feedback. So you have to use an amplifier, operation amplifier is fine, and you make basically, this is just a principle, reference voltage, you have a reference voltage, I draw here a battery, it's not a battery, it's an electronic circuit, it's for example a band gap circuit. You have a reference voltage. This circuit is a closed loop negative feedback system. You have the inverting input on an op-amp closed in a feedback system and it is stable. The negative input follows the positive input. So the positive input is a VREF. This is a very precise stable voltage that I make with a band gap voltage source, voltage reference. And my output voltage will have the same voltage as VREF. But from the output voltage you can get a lot of current because you have a power amplifier. This is linear because this transistor works in linearity. Linear systems have, linear power supplies have inside, let's say, resistors, capacitors, amplifiers, transistors. Well, transistors are also inside the amplifier. But this transistor works in linearity. It means it has, it is in, probably you thought if you had an Italian class, what is the name of active region, direct active region, something like this, RAD. Regione attiva diretta, active region.
Direct active region.
Direct active region. If you are in the direct active region, you have power dissipation because you have a voltage across the transistor and a current flowing through the transistor, and V times I is power, so it dissipates. On switch mode converters, any converter, not DC to DC or DC to AC, anyone, you have input power, output power, N, P naught. Inside, you cannot use any component wasting power, heating up on purpose. So, capacitor is a good component to be used over there, because capacitors don't dissipate, ideally at least, any power. Can you use transistors in the active region, in the direct active region? No, because transistor in direct active region is dissipating power. You can use transistors, you have to use transistors, MOS or bipolar, whatever you want, but only as a switch. Either the switch is open or it's closed. If it is open, how much current flows through an open transistor? It's more or less like asking what was the color of the white horse of Napoleon?
White.
Zero. So zero current times voltage is zero power. When the switch is closed, you have current flowing through the switch, but you have basically no voltage across the switch. Yes, a little bit there is voltage, but the power dissipation is very limited. So switches are okay, capacitors are okay. What about signal amplifiers, so bands? Yes. Those are not high efficient components, but they take so minuscule, so small power that we can go, and in any case we need some electronics, so we have amplifiers for feedback loop or for whatever you want. What else? Can we use resistors?
No.
No, because resistors are good for making heating systems, but not for power electronics. No resistors. And we are forced, that is the bad news, we are forced to use inductors. No way to do a power supply, a switch mode power supply, switch mode converter without inductors. And too bad. Why? Well, probably you know this old problem. You have two capacitors, two same value. This is initially charged at V naught, this is initially charged at V equals 0. And you close the switch, what happens? The charge that is stored at this capacitor, and the charge is V naught times C, just redistributes between the two capacitors. It just goes partially in the other capacitor. The charge is conserved. The charge is constant. Charge was initially V naught times C on this capacitor, and at the end, after you close the switches, the charge will stay the same. Why? Because electrons have a very good property, they don't jump out from the wires, fortunately. Electrons stay in the wire, except in a few cases. So at the end, you will have double capacitance, same charge, 1/2 of the voltage. The final voltage, V final, will be V naught over 2. Did you already see this problem? Yes, it's a classical problem for all electrical guys. Yes, no? Say yes, please. What's the trick? What's the bad part? If you evaluate the energy over here, you get that the initial energy is 1/2 V naught squared times C. The energy at the end, you have two charged capacitors, is twice times and what? V naught over 1/2 squared, and you find out at the end that the total energy is just 1/2 of what you had at the beginning of your calculation. Twice because you have two capacitors, of 1/2 because the energy in a capacitor formula requires this 1/2 of what? C, still the same C as before, times V naught over 2 squared. V naught over 2 squared. And the final energy, this is the energy of it in each single capacitor, times 2 because you have two charged capacitors. The final energy is equal to These two and these two cancel out, and you get 1/4 of C V naught squared. Oops, we start with 1/2 V naught squared C, and we end up with 1/4 of V squared, 1/4 V squared C. We lost half of our energy. Where is this energy? Well, there are many different ways to explain this apparent problem. The fact is that every time you connect in parallel two capacitors or two voltage sources, a capacitor and a voltage source, you will waste energy. What you have to do is, if you have to charge a capacitor, you must charge it with a current source, not a voltage source, or you have to charge it with an inductance. If you put here an inductance and you got the switch, you don't have two capacitors in parallel anymore. You have a resonant circuit. This circuit starts to resonate, and it can transfer energy from one capacitor to the other capacitor without wasting energy. So, in order to get high efficiency, we need to use inductors. Inductors are not good components. We don't like inductors because they are large, heavy, they have losses. Capacitor is quite better compared to inductor with the loss, from the loss point of view. But we are forced to get high efficiency, we need inductors. No way. Too bad. So, switch mode converters, switch mode conversion needs capacitor, inductors, no resistors, and switches. What are the advantages and disadvantages going on the switch mode conversion and going on the linear conversion? Well, the first difference, I put here a plus, meaning a good thing, and everything I write on this board will be exactly the same on the right board, changing the sign. So if this is a plus over here, it will be a minus over there. It will be a negative point over there. What is the very good advantage we get from a switch mode conversion? That means we don't use, we use switches, we use inductor, capacitor, no resistors, no linearity, no transistor linearity. Efficiency. We have no elements wasting power at this idea. So, a big plus is efficiency. This is the main reason why power converters are used. This is the main reason why you are here in this class. Well, no, not why you are here in this class, but why this class exists. Efficiency. That's important. It's very important. Because just consider any AC adapter you have. The AC adapter for your cell phone, the AC adapter for your laptop, they have a size. The AC adapter for a cell phone could be something so small. If it had to be built using linear technology, it would be at least this size and weighing far more. And the same story for all other power supplies. So efficiency with all the advantages I told you about earlier. That means weight, cost, temperature, etc. Second reason. So here, if we do the same list, this will be a minus, negative point, efficiency. Because we have a transistor in linearity, voltage across collector emitter, current flowing through it, V times I makes P, power. Then, another positive aspect for switch mode conversion. It's easier to explain starting from the negative, the corresponding negative over here. If you look at this circuit, you have the collector has to be more positive than the emitter. So means if current flows down, you have voltage drop with the positive on top. The output voltage has the same polarity as the input voltage. If this is positive with respect to the ground, this is positive with respect to the ground, cannot go below zero, and the output voltage is smaller than the input voltage. You can only go down in voltage if you have a linear conversion. If you have a switch mode conversion, we will see that you can have an output voltage that is V naught, not related in magnitude and sign with the input voltage. You can have an output voltage that is smaller than the input voltage, exactly like in the linear case. But you have an output voltage that is smaller than the input voltage with high efficiency, without wasting power. Or you can have an output voltage that has opposite sign than the input voltage. It means you can have coming with a positive voltage and get a negative voltage at the output, referring to the same ground. Or you can have an output voltage that is larger than the input voltage. You start with a battery that is 1.5 volts in your MP3 player, and you can boost up this voltage to 3 volts, 5 volts to drive your headsets and to make you deaf with a very loud music in your ear. Or you can have the output voltage that is isolated from the input voltage. You can have an isolation. That means the input voltage can be connected to the mains. That means if you touch it, you get a shock, electric shock. The output voltage you can touch and you are isolated. And so on. You can have, this is not a real big difference with respect to the linear side. You can also do the same with the linear side, but you can have multiple outputs. You can also have multiple outputs of that. Just repeat the circuit many times for each output you want and you get a different voltage. Here it's a little bit easier. Oh, I do repeat. What did I write here?
Efficiency.
Efficiency. What do I mean with efficiency? Cost, size, weight, life, temperature, and so on. This is all included, all hidden inside the efficiency word. Okay, let's go to the bad words, to the bad parts. Unfortunately, today I forgot in my office my color chalks. Those who had my previous class of circuit electronics know that I like to use color chalks on the board, and I will need it because when I will have some waveforms, many waveforms in the same graph, I need colors to distinguish them. So just take a couple of 3 or 4 different colors in your pencil pencils, and we will use it. Anyway, I can put it in red saying it's bad, but imagine it's already in red. There are a few negative points of switch mode power supplies, power converters, with compared to the linear systems, the linear conversion. And these disadvantages are that, first, these converters are complicated, difficult to design. I can teach you how to design a linear converter in probably 2 hours. I need 60 hours to teach you how to design a switch mode converter. You need at least 1 class of power electronics, better 2 classes. Once upon a time, when this class was 120 hours in a semester, the class was sold satisfied, or how is the commercial say? How do the commercial say? Satisfied or money back? Well, I can give you money back, but I was selling this class a long time ago with guaranteed that you were able to design something reasonable. And I said, if you have problems the first 2 or 3 years of professional life in power electronics, just give me a call and I will help you without any problem. I can't do it anymore, because with 60 hours, you cannot reach exactly the level of being a good designer of power electronics. You will have a very good understanding, but you will need some extra information. So I can select satisfied or help because it's not enough. Unfortunately, they gave me 6 units, 6 credits, and I can do so much. Complicated. Quite complicated. Second point is, so this is easy. Second difference is that both systems, both the linear and the switch mode converters, are feedback systems, system with a feedback. And you know that a very important parameter, oh, by the way, parameter, not parameter. Italian guys, parameter. Is somebody here that is English mother tongue? You are English mother tongue?
Not exactly, but I speak English.
Yeah, okay. Yeah, seems like Indian accent, Malaysian accent.
I'm Indian.
Yeah, okay. Meanwhile, I forgot why I asked this. Oh, how do you say parameter?
Parameters.
Parameters?
Yeah.
No, parameters. British is parameters, English is parameters. Parameters? No, parameters.
Maybe in the US is parameter, in the UK is parameter.
No, I think in English, in Britain it is parameters as well. Oh, by the way, I never had formal lectures of English. I never learned English at school. I learned on the road. So, and on the California road. So, my English is slightly biased toward the American English. Anyway, both these systems are feedback systems, system with a feedback. And you know that an important parameter of a feedback system is stability, is phase margin, but the important one is crossover frequency. Crossover frequency is that frequency making a boundary between the system makes what you want, the system behaves very good, fast, etc., from the system makes what it can. It's not respecting the specs anymore. And this crossover frequency basically gives you the speed of the system. How much time does it take to return on the steady state condition after you have a change in input voltage or output load or whatever it is? Well, those linear systems can be, I said can, I don't say they are like this every time. That can be fast systems. You change the load, the output voltage moves, but it recovers immediately. And this can be slow system. Slow does not mean that it takes half an hour to recover to the original value. It means that it's slower than an analog system. Slow, that means FC, crossover frequency of your feedback system, FC is smaller than the linear system. And we will see when we will design the control part of this switch mode converter, we will choose this crossover frequency. I'll tell you how to choose this crossover frequency. This will be our design law. It will be slow. Too bad, guys. You get all these advantages. You have to play. The last main difference between these linear and this switch mode converter is electromagnetic noise. Here, the electromagnetic noise is very low, basically inexistent. It's a silent, it's a very quiet sound. It does not make any noise, any disturbance. Here, your electromagnetic noise is very high. A switch mode converter is a very good source of any kind of noise you can, and disturbance you can imagine, and more important, of any kind of noise you cannot imagine. Yesterday, I was in a company here around just outside Torino, trying to fix a power converter that was making too much noise. problem of electromagnetic compatibility are very difficult problems to solve. It takes a class on electromagnetic compatibility. But these switch mode converters are very noisy circuits because every time the switch opens, it closes, opens, because it generates a very steep voltages, very steep edges in voltage, very high DVDT or VIDT signals, and you have noise, a lot of noise, any kind of noise you can imagine, and also those that you can't imagine. And yesterday I started to work on that circuit at around 2 p.m. At 7:30 I was still trying to fix noise because I was fixing the noise in one point and it was coming out from the other side, and it was like catching a lot of mice going spreading all around. This is a big deal. Okay, let's take a 5 minutes break.